Okay, so in our last meeting, we talked about Deutsch algorithm, and Deutsch-Jozsa algorithm is just an extension to Deutsch algorithm. Okay. In this case, we have n-bit inputs, and then it goes to either 0 or 1. You have got 1, 1, 1, and all of them could be 0. So there are two constant classes. In other words, it could either be all of these inputs, like when you have a function that takes this as an input, and therefore, if it's a constant function, that means one of these outputs could be a possible output. So therefore, it can either map to all of these inputs to 0 or 1, so there are two possible constant cases. Okay. In the balanced case, we have the same functions. I mean, like this is one of them. Okay. Then there are 2 to the n, if this is n, there are 2 to the n outputs, and those are mapped. So we could actually have here half of the outputs is 0 and half of them are 1. So for example, one choice could be 0, 0, 0, 0 to the n minus 1, and then we have got another set of ones that are also 2 to the n minus 1. So the total is just 2 to the n. And you can have, of course, the different mappings here, okay, such that half of them are 0 and half of them are 1. This mapping has to be 1 to 1, of course. Okay? But so it's essential that half of the output is 0, half of the output 1, so we can call it balanced class. In fact, there are 2 to the n, you choose 2 to the n minus 1 possibilities, okay, for this mapping, and that's the number of balanced functions you have for n-bit input functions. So if you have n equals 3, right, then you have, of course, if you put it here, 3, it's 8, this is 4, so you choose 4 out of 8, so there are many of those balanced functions. So the question is, if n equals 3, what's the classical approach to figure out whether a function is balanced or constant? Well, in order to do this, you have to, of course, ask questions. In the worst case, you have to actually spend all of these 2 to the n minus 1 in the worst case. So that means, in order to differentiate between this case and all 0 case, for example, take the all 0 case. Okay, so let's suppose that it's constant 0. Okay, in order to differentiate these two, you have to ask all these questions that gives those outputs, which is 2 to the n minus 1, and then one more, either this one or some other one, in order to differentiate that this is a balanced class, not a constant class. If you ask, for example, in the worst case, 2 to the n minus 1 questions or 2 to the n minus 1 inputs, so you query the same function 2 to the n minus 1 times, and then you ask another question, extra question. If it is 0, then it's a constant 0, right? If it is 1, then it's a balanced class. So in the worst case, you have to ask at least, but the worst case, of course, at least 2 to the n minus 1 plus 1 queries. Okay? In order to, certainly identify this function to be a balanced or a constant class. Okay, that's the worst case, of course. Well, if you're lucky, for example, you ask, what's the output for this particular input, you get 0, for example. And then in the second question, you ask, what's the output of this? And then the query result says 1, then you're done. It's a balanced class. You have 0 and 1 both at the same output, as an output for the same function. Therefore, that makes this function as a balanced class. So you only ask 2 questions, 2 queries, in the best case. But in the worst case, it's exponential. Complexity is exponential. So the Deutsch-Jozsa algorithm, or a Deutsch-Jozsa function, so let me just draw the function that implements this Deutsch-Jozsa algorithm. We got n, we got x0 chronicle, and then another chronicle, xn minus 1. And we have y, of course, here. Okay, so this is the construction of the gates with n plus 1 inputs and n plus 1 outputs. This is reversible, of course. Okay, and the output here is y XOR f function x0, x1, xn. Okay, that's the function we have. It's pretty simple, and the Deutsch-Jozsa algorithm is an extension to the Deutsch-Jozsa algorithm. In the Deutsch algorithm, if you remember, we got only 1 qubit in the top and 1 qubit at the bottom of the circuit. But now we have, of course, n qubits in top, n qubits, that goes to a Hadamard gate, of course, raised to the power n. And then we have this f, and this is the y, which is 1. Okay, and then this, again, these are all n qubits. This goes to another Hadamard, raised to the power n, and then we got this measurement for each one of these qubits. There are n qubits and n measurements here, and we have this, again, output that comes out of this circuit. So we actually analyzed this in our last meeting, and we finally figured out that it's pretty simple. It's just a straightforward extension, the Deutsch's algorithm, because we finally, in general, we finally get an unentangled qubit. These qubits are unentangled, and let me just write it down here to show you the result, directly. The result is in general 1 over 2 to the square of 2 at 2 to the n, okay, and then they're all sums. And sum starts from I1 to 0 to 1, and then another I2 to 0 to 1, and we have IN to 0 to 1. These are all digital, and minus 1 raised to the power f, I1 to IN, okay, and this I1 to IN. These are all digital, 0 and 1, and chronicle delta squared check 0 minus check 1. Okay, it's pretty simple to Deutsch because we already have this term in the Deutsch algorithm already, and this term here is the generalization of for the n qubit case. All right, and so this is the generalized version. I think I actually have a missing 1/2 here. Okay, all right, so that also needs to be there. And so if we have this, and we finally realize that. When we pass this in, this is showing us that the last qubit actually is unentangled, okay? Unentangled. With the rest of the n qubits on top here. Okay, so when you pass this through a Hadamard gate, then, for example, for n equals 2, okay, you will realize that what you will get actually is 1 over 4 minus 1 to the power f0, 0. For example, I'm actually giving you an example for n equals 2, just to simplify the representation. So we got minus 1 raised to the power f 0, 1, and we have plus minus 1 raised to the power of 1, 0, and minus 1 f1, 1. Okay? So apparently you see that if f is a constant, if this is a constant function, okay, this is the top qubit, by the way, all right? So you see there are n of those, right? I'm talking about the top qubit, this one. And you will realize that this top qubit, by just measuring the top qubit, we can identify whether it's a constant function or a balanced function. The reason being is that if f is a constant function, this means f could be all zeros. In this case, this is minus 1 raised to the power 0, which is 1. This is 1, this is 1, this is 1. So 4 divided by 4 gives you 1. Okay? So if f is constant, this could be either 1 or this is 1, 1, 1, 1. Minus 1 raised to the power 1 gives you minus 1. Minus 1, minus 1, minus 1, minus 1 is a minus 4. Divided by 4 gives you minus 1. So therefore, in either case, if you measure it, okay, you will actually get, with probability 1, all zeros, okay? In other words, not just the top qubit, but all of them, of course. You have to measure all of them. But what that means is that if you measure all of them, and then you get a result 0, 0, 0, 0, 0, 0, all of them 0, okay, all of them 0 with probability 1, then it's a constant function. Okay? If you get something else, for example, 0, 1, 0, 1, 1, for example, then you know that it's a balanced function. Because for constant functions, this has to be either 1 or minus 1. Because remember that if f, this function is balanced, that means this would be a 0, right? So therefore, if this is 0, that means 1 over 4 multiplied by 0 gives you 0, and the measurement result will be 0, not 1. Okay? So therefore, you will actually have to see, a probability, with probability 0, this 0, 0, okay, we don't see 0, 0 at the output. In other words, the measurement result cannot be 0, 0 for n equals 2. For n, general n, all zeros happens with 0 probability. So therefore, you never see this if it's a balanced function, right? If it's a constant function, then you always see this, all right? So therefore, by just looking at the measurement outcome, you can identify whether the function f is a constant function or a balanced function. This thing actually follows, this plus 1, plus 1, plus 1, plus 1, follows from the Hadamard gate, right? The Hadamard, if for n equals 2, Hadamard 2, right? Sorry. Actually is given by 1/2, right? 1, 1, 1, 1, and it's 1 minus 1, 1 minus 1. Remember the Hadamard gate? So this is 1, 1, minus 1, minus 1, and this is minus 1, 1. This is 1, minus 1, and minus 1, minus 1, minus 1, 1, right? This was the Hadamard. When you just take the chronicle product of two Hadamard gates, you get this particular matrix. So what you're basically doing is you basically multiply these 1, 1, 1, 1. That's why we got plus 1, plus, plus, and plus. Okay? Okay. Anyway, so this is the generalization of... Yes, we have two Hadamards here. There's an n. So in this general case, we got n qubits, right? 1, 2, 3, 4, whatever the n is. That means each one of the qubits passes through a Hadamard gate. Okay? So we got, for n equal 2, there are two Hadamards. One for the top qubit, one for the bottom qubit. Okay. We don't touch here. Okay, this qubit is just free. All right, so this is, as I said before, is a generalization of the Deutsch algorithm. The only difference between Deutsch and the Deutsch-Jozsa is that the number of bits of the function input, the number of input bits for the function is n. In Deutsch formulation, n was stick to 1. Okay, let's just move on to the next algorithm called Simon's algorithm, right? Those algorithms are quite basic, and one of the alluring things about these algorithms is that you can find their applications in different engineering domains. Okay, particularly in machine learning, or matrix evaluation or polynomial evaluation, okay, which are quite commonly used in different engineering disciplines. Okay, so in Deutsch and its extension, we actually had two properties. One of them is that final answer was found with a single query. Okay, that was the first property. Okay, properties of Deutsch and its extension. Properties of Deutsch algorithm. Okay, first property was that final answer is found with a single query. we have time here. Okay. Okay, so final answer is found with single query. The second property was final answer is found with certainty, right? Certainty. There is no probabilistic arguments, unless there's a noise, of course, right? Noise associated with gates, noise associated with the function that we implemented, to turn it into a quantum realm. If there are no noise in an ideal world, ideal case, we always assume that probabilities are, perfect. So therefore, when you measure something, we see, for example, all zeros at the output of Deutsch-Jozsa algorithm, all zeros with probability either 1 or 0, depending on the function being balanced or constant. So therefore, these two properties are quite nice. I mean, they're very attractive. However, because it's single query, we know that it is exponential query time, query complexity, when it's a classical algorithm trying to resolve whether a function is a constant or a balanced class. And we do it with certainty. Okay, these are great properties. However, most of the algorithms are not like that. Okay, most of the algorithms actually are going to give you with the right result, correct result with high probability, but not with certainty. And their queries might be just few, not just a single query. Okay, and it turns out that Deutsch and Deutsch-Jozsa algorithms are applicable only to limited number of problems, such as the problem that we just discovered, we just considered in our last meeting, as well as in today's summary. Therefore, in order to expand the number of classes of problems we would like to attempt applying those algorithms, we need to really give away, some, to a certain degree, some of those properties. Okay, so instead of looking for a single query map, maybe we can actually ask or allow the algorithm to use few attempts of queries. Or we can allow some probability of making mistakes. Okay, so this is going to also expand the class of problems that we would like to attempt applying. So therefore, this example that I'm going to show you is going to actually do that. It's going to actually particularly reduce the probability of being successful to a number which would be acceptable. However, it's not going to give us, with certainty. Okay? And we will not just do a single query, we will ask actually a couple of queries rather than a single query. So here's the question. Okay, and this is kind of applicable to cryptography and also, hacking a specific key or extracting a key from an information. So this could be really applicable and to a real world where security algorithms or protocols are used. So that's the definition. Here's the definition of the problem. Suppose we have a function f, okay, function f, and f is as follows. We have x0, xn minus 1, so it's n bits, okay, and that gives us another n bits, y0, yn minus 1, okay? And for all xi, yi, these are all from the binary domain, okay? These are binary fields, okay? And that there exists in S a sequence of n bits. Therefore, S is f2n. Okay, so S is n bits long. That exists at this sequence, a binary sequence, S, such that I've got S dot and ST to stand for such that. We've got fx equals fy, if and only if x equals y, right? Or x equals y, this is certainly gonna be equal. Or we have y equals x XOR s, okay? So this has a kind of bridging between these inputs and outputs, x and y, okay? So when you have a bitwise XOR with x, you get a y, and this equality is satisfied. This is a special sequence, S, okay, that does that. that specific equality. So, let me give you an example. Let's just take n equals 3. Okay, simple, plain and simple. And assume s is equals to 1, 1, 0. What does that mean? Well, that means the following. We have 0, 0, XOR with 1, 1, 0. That gives us 1, 1, 0, right? So, according to this definition, this basically means that F00 equals F110. Okay? And let's just assume, because it's a function that maps m bits to n bits, let's just assume that this is 101, let's say. Okay? Let's just do it for the other 001 XOR with 110. We got 111, right? And this is going to... As I said before, that if you look at these inputs and output pairs in general, when you have n bit input for this function, you actually, in the worst case, have to ask 2 to the n-1 questions, in the worst case, and get different answers. And you need at least one extra question or query in order to figure out one of those pairs, in other words, the same output, so you can go back and apply this to figure out s. Okay, so in the classical case, I expect to find the output with certainty. However, you need 2 to the n-1 plus 1 queries. That is exponential query time, or query complexity. So, which means that we may have to come up with a better algorithm that provides us at least not an exponential time complexity, or query complexity, sorry, but maybe we can play with the probability of finding s, okay, not with certainty, but with high probability. So that's this Simon algorithm all about. So we've actually asked this question, and our query complexity using classical approach is exponential complexity. Okay, so our approach to this problem is, it came from Simon's, and that's why people call it Simon's algorithm. Okay, so let me erase this part as well. Simon's algorithm provided, okay, a polynomial time procedure that helps us develop an answer for this question, finding, without knowing what f is, finding x. Okay, that's the gist of the question. Before I, explain the details of the Simon algorithm, I would like you to bring something to your attention about the Hadamard gates. Okay, so let me just show you a matrix. Okay, this matrix is quite relevant to our case. 0, 0, 0, 0. I'm going to just show you 4 by 4, but you can actually introduce, think about the more expanded and general version yourself. 0, 1, 0, 1, and this is 0, 0, 1, 1, and I've got 0, 1, 1, 0. Okay? And I want you to name those rows and columns by 0, 0, 0, 1, 1, 0, 1, 1, and this is 0, 0, 0, 1, 1, 0, I'm sorry, 1, 0, and 1, 1, okay? So, look at this particular special pattern. And this is actually going to be tied to Hadamard, okay? Multiple Hadamards, actually, okay? Soon, very soon. But before that, I want to actually bring something to your attention. That each one of those entries in the matrix actually is a dot product of the rows and columns. For example, take this one. What is this equal to? This is actually 0, 1, dotted with 0, 1, right? Which basically means 0, 0, XOR 1, Dot means and. So 0, 0, multiplication or AND operation is 0. And XOR 1, is 1. So that gives you 1. Okay, that's why you have a 1 in this particular entry in the matrix. You can actually verify that for every entry in the matrix. Okay? So this basically can be written as, pretty simple, written as the following, right? Like, for example, here I have a dot product of 0, 1, 0, 1, right? So this basically means that Yeah, so instead of writing this way, so let me write it this way. So I'm going to connect this to Hadamard gate, okay, before going any further. So in the Hadamard case, for example, think about the Hadamard, okay, raised to the power 2, okay? That's Hadamard, okay, tensored with itself. Tensored with itself, Hadamard squared. Do you remember that? You probably remember that. This is 1/2, right? 1/2, 1, 1, 1, 1, 1, 1, 1, minus 1, this is minus 1, sorry. Okay, and then 1, 1, 1, minus 1, because these are all Hadamard, and this is minus Hadamard, right? So this is minus 1, minus 1, minus 1, 1. That's my Hadamard, original Hadamard. Now you can actually recall, compare these two matrices. You can actually write this, okay, as follows. 1/2, right? Minus 1 raised to the power 0, 0, dot 0, 0. Minus 1 power raised to the power 0, 0, and 0, 1. And so on and so forth, right? Because this is going to be also 0. This is going to be also 0. Okay? Because when you dot product, take a dot product with 0, 0, you always get 0, right? That's what. And this is going to be minus 1, 0, minus 1, 1, minus 1, 0, minus 1, 1. Okay? You see these? These are going to be your exponents, actually. Okay? Minus 1, 0, minus 1, 0, raised to the power 0, and minus 1 raised to the power 1, and minus 1 raised to the power 1. And finally, we got minus 1 raised to the power 0, minus 1 raised to the power 1, minus 1 raised to the power 1, and minus 1 raised to the power 0. Okay? And all of these exponents are just the dot product. Okay? These two, for example, or these two, or these two. Okay? So therefore, you can actually use the entries of this matrix, assume them to be the exponents of the minus 1. And that's going to give you the Hadamard gate. Okay? So it's pretty simple to calculate an entry, for example, this entry of a Hadamard square. All you have to do is just to take the row and column index, okay, which is 0, 1, and 0, 1, okay, and so you figure out the exponent, right? Then you will gonna do this, 1 over square root of 2. What is n? Is 2, okay, minus 1 raised to the power of what? The dot product of the 2. 0, 1, and 0, 1. That's gonna give you what? 1 over 2 multiplied by 1, which is 1 over 2. And that is the entry at that specific point. Well, in this case, of course, this is 1, sorry. So this gives you minus 1, that's give you minus 1 over 2. Sorry about that, that's my mistake. Okay, so that's minus 1 over 2. Why? Because you can see that it's minus 1 over 2 right here. It's pretty simple for, to visualize. It's quite simple when you have a Hadamard which is tensored with itself. But if you have a Hadamard that is tensored n times, okay, h, n, then that is the problem, because if I ask you a specific entry of this matrix, it's not that straightforward. But I'm now giving you a procedure that gives us that number, specific number, for any general n. Okay, that's why I wanted to, bring this to attention. For example, another example, let's suppose that we are looking forward to find out some entries of h, tensored with 5 times. So 5 times. Okay? And I want to know the entry 0, 0 row, this is row, and 1, 1, 1, 1, 0, 0, the column. Okay? You see, it's a 5 by 5. I'm sorry, sorry about that. It's 2 to the 5, 2 to the 5, which is 32 by 32 matrix. So each row and column can be encoded with 5 bits. So if you take the dot product of the two, you get 0, 0, and 1, and 0, 0. If you XOR them, you get 1. So therefore, the particular entry, that the intersection of the row indexed by this number and the column indexed by this number is going to be given by 1 over square root of 2 raised to the power 5, because now n is 5, right? Minus 1 raised to the power of the dot product of the 2. Okay, which gives you, since it's 1, which gives you minus 1 So it's minus 1 over square root of 2 raised to the power 5. That is the entry. Okay? At that particular entry of the matrix 32 by 32, that corresponds to the Hadamard tensor with itself 5 times. Okay? Alright, so now, having recognized that, I'd like to extend this discussion to the following observation. Okay? That's important. Because once we make that observation, why did we discuss all that will be much more clear to you. Alright? Okay, here is the reason. So let us focus on adding 2 columns of H. So adding 2 columns of Hn. Okay? I would like to add the 2 columns of the Hadamard matrix tensored with itself n times. Okay? And those columns are not just 2 random columns. Those are the columns that are paired by S. Okay? In other words, you remember the S? You got, for example, X to be 5 bits long, let's say, if n is 5. And then Y, another column that is also 5 bits. But Y equals X, XOR S. Okay, 2 columns indexed by X and Y. That's the pair, definitional pair. Okay, so now I'm going to have, let's just use, since I use X and Y in different places, I'm going to just change this to B, say, and B XOR S. Okay, I don't need to call it another thing. So this is B and B XOR S. Okay, now let us just illustrate what I mean by that. Let us assume, as we always do, simple case, n equals 2. Okay, and S is 1, 0. Okay. Now in this case, I have F00 equals F10, and let's just suppose that it's 0, 0. And I have F01 and F11, they're all equal, and I'm going to assume them to be 1, 1. Okay? Now, if you look at the Hadamard tensor with itself, we got the following: 1, 1, 1, 1, 1, 1, minus 1, 1, minus 1. Well, 1, 1, minus 1, minus 1, and we got 1, minus 1, minus 1, 1. Okay, that's the Hadamard of corresponding Hadamard, actually, which you can actually find entries through this logic. Okay? But if you add column 0 and 0, 0, okay, 0, 0 and 1, 0, okay, what you're going to get is 1/2. 1, 1, 1, 1, that's the 0, 0, 0 column, right? Let me just use another color for you to distinguish these columns, right? I got 0, 0 here, 0, 1, 1, 0, and 1, 1. Those are the column indexes. So I have 1/2, 1, 1, 1, plus, or XOR, 1, 0 column, right? This is this, 1/2, 1, 1, minus 1, minus 1. So what do we get? 1/2, 1/2, 1, 1. So what do we get? We get, absolutely. Let's just put 1/2 in front. We got 2, and then another 2 for this 2, and then 0 and 0, right? 0, 0. All right? Okay, and also you can do the other thing for the other pair, right? Like 0, 1 and 1, 1, which is these 2 columns. You can do the same thing and get the same, I mean, very similar result. Not the same, but it's very similar. Let's just do it. 1 minus 1, 1 minus 1, right? 1 minus 1, 1 minus 1. XOR with 1/2, 1, 1, right? So 1, 1 is this one, 1, minus 1, minus 1, and 1. So what do you get? 1/2. 1 plus 1 is 2. And minus 1, minus 1, minus 2. You get 1 minus 1, 0, and minus 1, 1, 0. Okay? You see, one of the things we realize is that if you take the absolute value, these are going to be 2, 2, and 2, 2. The reason that we're getting zeros here is because that those rows here that are indexed by 1, 0, and 1, 1, right? The reason that we're getting them 0 is because the top dot product with these, for example, 1, 0, right, take 1, 0 for example. This is 1, 0 dot product with 0, 0, which gives us 0. And we got 1, 0 dot product with 0, 1, which is 0. And if you got 1, 0 dot product with 1, 0, that gives you 1. And you got 1, 0 dot product with 1, 1. These are row indexes, by the way. This is column index, this is row index. And you got 1 again. You see, whenever you have a dot product of 0, then you have got non-zero values. When you have a dot product of non-zero, then you got 0 values. Okay? And same here. You can actually verify that. Okay? That's one of the things we realize about these entries. Okay? So in general, this is an example, of course. So let me write down what happens in general with n bits. Okay? In general, we select two columns paired by S, just like this one, and then say that B and B XOR S, okay, these two columns, using row R, A, not R, A, let's suppose I use A, row A, again this is binary, where A, B, S, they're all in n bits in F2n. In this case, n is 2, right? But I'm going to just assume it to be n, okay? In this case, I'm going to just write the following. A dot product B XOR S, which I can actually write it as A, B, and minus 1 A, S, right? And this is going to be equal to, actually that would imply that minus 1 A, B XOR S and minus 1 A, B, right? These two actually are going to be equal to each other if S is 0. Okay? I'm not just S. I mean, not just S, but A dot S. The dot product with A is going to be 0. Just like here. Right? If the dot product is 0, then it's going to be equal to, B XOR S and B are the same. Okay? It's just about A and S having a dot product 0. Okay, so they are going to be equal, so these are equal if A dot S is 0. Okay? In other words, the dot product is 0. And they are different if A and A dot S is not 0. Okay? In other words, 1, right? Let's just be more specific. 1. Alright? That's pretty much it, actually. That's the observation we have here. If S is, this is S, and these are A's, by the way, right? These are A's. So if S and A has a dot product 0, then we have minus 1 raised to the power A, B XOR S, or B, is going to give you the same results. That's why we have 1 and 1 here. Okay? One of them is the original, which is 0, 0, and the other is the B XOR S. They're equal, do you see? They're equal. And here is also they're equal, right? And here, let's see, but for example, look at this example. They're 1, 1, and minus 1, 1. They're equal. Okay? And since they're equal, you get either 2 or minus 2. You see? That's exactly what this is saying. If they're equal, then they actually sum together to generate these 2's. Or in general, they're going to create 4, 8, 16, larger numbers. However, if they are not equal, in other words, if A dot S is 1, then they're going to cancel each other out. You see, if they're not equal, 1 minus 1, 1 minus 1, or 1 minus 1 minus 1, 1, if they're not equal, they cancel each other out. They become 0. Okay? Because their dot product is 1. Okay? You see? This one. So this is the observation we have. And finally, what I just said is A dot B XOR S plus minus 1 A dot B. This is what exactly I'm doing here, adding the columns. You got plus minus 2. You either get 2 or minus 2, depending on whether these are 1 or minus 1. But they're equal. In the other case, minus 1 raised to the power A, B XOR S. Of course, this is true for n equals 2. plus minus 1 a dot p, which is equal to 0, right? So this is if a dot s is 0 and if a dot s is 1. A dot product with s 0 and a dot product with s 1. Okay, so here we observe this is true because, rows cancel each other out. Okay, as you can see in this example. All right? All right, so now, after having observed this phenomenon, okay, I'm going to just erase, particularly this one is important because this is for general n. But now next I'm going to just draw the circuit, the Simon circuit, this Simon's algorithm, okay, here. Now you realize that how important this observation is because we're going to be using it to figure out the S, okay, using a few queries. Okay, first before I draw the circuit, I need to draw the gates, right? That helps us develop this function, right? This is the function that is, we don't know about the function. We don't know the S. This function actually is a function of S, right? When you talk about this function is depending on S. So somebody picked up the S and picked up those outputs and generated this function for you and tells you, tell me S. Can you find S? So you can connect anything to this function. But let me just briefly describe what this function is about. x0, x1, so it accepts n inputs from the top. So there are n qubits, and then there are n qubits at the bottom, y1 to yn minus 1. That goes in, and we have n here, x0 to xn minus 1, and we have n here, y0 to yn minus 1, okay, and then we have xor, f, x0 to xn minus 1, okay? Okay, that's the output. This is bitwise XOR, okay? Bitwise XOR. In other words, this function generates some outputs, right? Like in n equals 2 case, we got 0, 1, 1, 0, whatever. And this is also another 2-bit, so you actually do it bitwise XOR, okay, to generate the output. Okay, so this is the function. And somebody designs this f, okay? And we don't know about f, as I said before. And that design is dependent on s. Okay, so the following is the Simon's algorithm or circuit. Okay, that's resolves this issue. So in the Simon's algorithm, we use all zeros and bits, and qubits actually, and qubits, that goes into a Hadamard gate. You see, we use Hadamard gate all the time because of its, putting the state to a superposition, so we can use that superposition, for our own good. You got these zeros, okay, and this is also n bit, n qubit, and the output is also going into another Hadamard gate and another measurement, of course. And these are all n qubits, and this is also n qubits. So it's pretty simple actually. We connect a bank of Hadamard gates here in the input, a bank of another set of Hadamard gates at the output, okay? And then we query this on the superposition and see what happens, okay? Now, of course, analysis of this circuit with a general n is quite complicated. So instead of doing that, I'm going to just focus on, n equals 2 case, if that works for everyone, okay? So let's just focus on n equals 2, and then maybe we can generalize it. So for n equals 2, we have 0, 0, right, going into the Hadamard gate. So therefore, we have the following, right? So 0, 0 going to the Hadamard, 2 Hadamard gates, giving us the following: 1 half 0, 0 plus 0, 1 plus, that's the super duper superposition state, right? 1, 1, 1. That's the output of the Hadamard. Now, if this inputs, output of the Hadamard input to the function, so this input goes in, of course, with also another 0, 0 for the y, okay, so for these two, Okay, so there are 4 qubits going in actually to the function. All right, the function output, this is going to be, of course, same as x. So this is actually same here of this. So I don't want to write it again. However, the output here is going to be the function itself. However, of course, one of the things that we realize about this is that we have the function. So the function output here, let me just write it down real quick. We have 1/2, okay, 0, 0, tensored with f 0, 0, okay? And plus 1/2, 0, 1, tensored with f 0, 1. Okay? And we have another 1/2, 1, 0, tensored with f1, 0. And finally we have 1/2, 1, 1, tensored with f1, 1. Okay? And that's it. Okay? That's it. Why is that? Because here, you see, y's are all 0, 0, right? So here 0, 0. That's why XORing with 0, 0 has got no effect. That's why we actually get f0, 0, f0, 1, f1, 0, f1, 1. And that's why I'm actually tensoring this with input 0, 0, input 0, 1, input 1, 0, input 1, 1. You see, because you can actually think about this, term by term because of its linearity, right? Okay. Anyway, now we would like to consider the top 2 qubits here because they go through Hadamard gate here. Okay? So I'm going to write this, maybe rearrange the terms. Maybe I can rewrite here using a different color, maybe red. And I can rearrange these terms. Okay? How? The following way. I'm going to just, because you can think of this 0, 0 going through Hadamard gate. I know what that means, right? Maybe I can actually rewrite this as follows. This 1/2 and another 1/2 coming from the Hadamard creates 1/4. Okay? And then I have 0, 0 plus 0, 1 plus 1, 0 and plus 1, 1, right? This is for this. And then I have a tensor with f 0, 0. Okay? Okay, f 0, 0. So I actually handled the first one. For the second one, I have 1/2, another 1/2 coming from the Hadamard, so it's 1/4. The Hadamard will make 0, 0 and minus 0, 1, right? Plus 1, 0 and minus 1, 1. Cats. And then that is tensored with f 0, 1. Why we have got 1 minus 1, 1 minus 1? Because of the Hadamard gate second row. Okay? And similarly, you got 1/4 0, 0 plus 0, 1 minus 1, 0 and minus 1, 1 and then tensored with f 1, 0 and 1/4 0, 0 minus 0, 1 minus 1, 0 plus 1, 1, right? And tensored with f 1, 1. Okay. As I said before, the pattern comes from, these patterns 1, 1 minus 1 is 1 minus 1 minus 1, 1. These are all coming from the Hadamard matrix, right? Remember? Okay, now I can rearrange this terms, right, to write it again the following way. 1/4 0, 0. That means I'm going to just take the first terms, each one of the inside the parentheses, and then combine them. So we got 1/4 0, 0, okay, and this thing, right? So I'm going to just write it here. F 0, 0. Cat, of course, they're all cats. F 0, 1, cat. F 1, 0, cat. And cat F 1, 1. Okay, that's the first term, because I actually collected column-wise now instead of row-wise. Okay, now I got another 1/4. Now I connect 0 ones, right? So that gives me plus F00, right? Minus now, because of this minus sign, I got F01 inside the ket, of course, and I got another plus for ket F10 and minus 1 for ket F11. Okay? And similarly, I get the third 10 collection of 1-zeros. Collection of 1-zeros give me this column. So therefore, F00, F01 are plus, and F10 and F11 are minus. Okay, so F00 plus F01, they're plus, and the rest are minus. F10 minus F11, they're all inside kits again. And okay, so this is the final rearranged terms. The same expression, but written in different way, in using, column-wise. So now I'd like to use this expression for a specific example. This is general. In other words, specific example, meaning that I'm going to pick up S and a function f. Okay, then apply this to that specific example. So let's just suppose n equals 2, as I did here, and S is 1, 0, and then I assume F00 to be F1, 1, 0, very cool. And similarly, I have F01 equals F11. Okay? So for this particular example, I'm going to apply it here. Because why am I applying here? Because it says that F00 and F10, they are equal to each other. Okay? And these are also equal to each other. Okay? So instead of writing this way, I can actually write this expression as follows. 1/4, okay, 0, 0, and tensor, of course there are tensor signs here that I forgot to add. They're all tensored right there, because we are talking about 4 qubits here. So these are 2 and 2. So this is tensored together with the following 2, F00, and plus 2, F01, right? Why? Because as I said before, we have got F0 and 10, they're the same, so I use only F00. And F01 and F11 are the same, so in place of F11, I use F01. That's why I have 2 of the F01 and 2 of the F00s. Okay? And similarly, for this particular one, I can actually write 1/4, 01, tensored with 2 F00, and minus 2 F01. Okay? Again, minus sign, why? Because of these minus signs. I know that F00 and F10 are the same, so I use F00 here, so that makes it 2 F00. And I also know that F01 and F11 did the same. I use in place of F11, F01, so we got 2 F minus, actually minus 2 F01. Okay? That's good. And the rest of the 2 are just gone away. Why? Because F00 and F10, they're the same, but they cancel each other out, right? These are going to cancel each other out. And this is going to also cancel each other out. Because one of them is plus, this one, the other is minus 1. It's a minus. So we got F00 and F10, these are all going to cancel each other out, and these are going to cancel each other, so these are actually zeros. Again, the same way. Why did they happen to be 0? Because S and the rows that corresponds to these 2, okay, which is 10 and 11, right? Because if their dot product is 1, they cancel each other out. If their dot product is 0, then you get these 2 expressions, non-zero expressions. Okay? So therefore, if you rearrange them, okay, if you rearrange these 2, I don't know where to write. Maybe I can use this space to do that. Okay, if I rearrange these, using, like, assuming there are 4 qubits, 2 on top and 2 on the bottom, we actually can rewrite this as 1 squared of the 2 and 0, 0, tensored with 1 squared of 2 Okay, because of these twos, right? These two cancel this 4, makes it 1/2. So I actually put 1 square root of 2 in one double qubits and other 1 square root of 2 for the other double qubits. So I got F00 and plus F01, right? And plus 1 square root of 2, 0, 1, right? That is tensored with 1 square root of 2, F00 minus F01. Okay? This minus sign is due to this minus sign. This plus sign is due to this plus sign. Okay, it's just a rewritten expression, same expression but written different way. So when we measure the top 2 qubits, okay, top 2 qubits, when you measure them, you actually can see that we get 0, 0 or 0, 1 with half probability. Okay, because that's, if you look at this circuit, we actually measure the top 2 qubits, not the bottom ones. Bottom ones are here. Okay, but if you measure the top 2 qubits, you actually either get 0, 0 or 0, 1. Not 1, 0, not 1, 1. Because their probabilities are 0 due to the dot product. Right? Dot product with S is going to be 1. That's why they cancel each other out. That's why they don't appear at the output of the measurement. Okay? So that clearly shows us that when you measure the top 2 qubits, you get either 0, 0, okay, with 1/2 probability, or 0, 1 with another half probability. Okay? So in general, we get all strings of length n whose dot product with S is 0 with equal probability. This is for n equals 2 case. But in general, if you got n bits, n qubits, that means you're going to get all 2 to the n minus 1, right? Sequences that with dot product, whose dot product with S is 0, and they're going to appear at the output of the measurement with equal probability. Okay? So in this case, for example, it's 1/2 for n equals 2. Okay? For n equals 3, okay? Now you got 4 possibilities, so each one of them will appear at the output of that, at the output of the measurement with 1/4 probability. Okay? All right. So final words before we close. We haven't finished yet, unfortunately. Okay? We haven't finished yet because we still cannot determine S, right? We actually know that when you measure, when you query this and make a measurement, you'll get one of these with 1/2 probability. But is that the end? No. By just knowing one of them, we cannot determine S exactly, right? But we would like to know, we would like to find out S. So we got a property now, actually. For example, n equals 3, let's say. Just make things more fruitful and more colorful. Let's assume that n is not 2, but 3. And S is, let's suppose, is 0, 1, 0. Okay? That's my n, that's my S. Okay? Now, I'd like to find out what S is. So let's just make, so what are the probabilities, what are the possible outcomes? For example, could 0, 0 be outcome? Could this be a measurement outcome? We make, of course, now, since n is 3, we make 3 measurements. Could 0, 0, 0 be a possible outcome? Can you say that? Just look at the dot product. The dot product of this NS gives us 0. It gives us 0, right? 0, 0, 0, 0, 0, 0. So all of them are 0. XOR them, you got 0. So 0 means that this is a potential outcome. Okay? This is potential outcome. How about 0, 0, 1? Could this be a potential outcome? If you take the dot product with this, you get what?
0, 0, 1.
We got 0, 0, we get 0. We got 0, 1, we get 0. We got 1, 0, 0. XOR them, all zeros XOR together gives us 0. So that means the dot product with that input is 0. Okay? So therefore, this is also a potential outcome. As long as the dot product gives us 0, it's a potential outcome. Okay? So this is another potential, and that's another one, right? And of course, finally, we got 1, 0, 1. These are all potential for inputs that gives us dot product of 0. So these are going to appear at the output of the measurement. Okay? And each happens with 1/4 probability. This happens with 1/4, this is 1/4, 1/4, and this is 1/4. Okay? Each happens with 1/4 probability. How about 110? Can this happen? Well, if you take the dot product of S and this one, you got 1, 0, 0. 1, 1, you get 1. And 0, 0 gives you 0. So when you XOR them, you got 1, which is not 0. So therefore, this is not a valid measurement outcome. So the probability of this happening is 0. Because the dot product is non-zero. All right? So good, because now we actually can figure out using maybe this relationship. But instead of asking the one question, we should actually query this function more than once, right? Because when you just query this once and you get 0, 0, 0, you got no idea what the S might be. Okay? But if you ask more questions, maybe you can come up with the others and you can use that information. Because why? For example, if this appears, this actually says that, let's suppose that this is S0, S1, S2. Right? S0, S1, S2. That means, I don't know what S0 is. S0 could be 0 or 1. S1 could be 0 or 1. S2 could be 0 or 1. We don't know that. But when you have an input 0, 0, 1, okay? Remember that S is unknown to us. We're trying to figure out S. So this is your input. When you look at this input, that basically means S dot S0, dot meaning the AND, okay? XOR with 0.S1, XOR 1.S2. This is 0. That's what you can ensure, okay? Because the Simon circuit actually ensures that this dot product is 0. So that means this you cannot really say anything about S0 because there's a 0 here. But this is S2. So therefore, S2 is actually 0. You can find S2 if this is your outcome of the measurement. You can find S2 actually. You cannot find anything if the input is 0, 0, right? Because it cancels everything. But this is going to tell you something. Because if you do the same logic here, that is going to give you S0 actually. S0 would be equal to the outcome, right? This is going to be, yeah, so this is also 0, right? Because the outcome is 0, so S0 is also 0. How about this? This is basically telling you that S0 and XOR S1, S2, right, is 0. And that actually confirms you that, right? That confirms that. Because you already figured out S2 and S0, they're 0, and their XOR is also 0. Okay? So that is also true. So what about S1? Can we determine S1? Well, S1 cannot be 0 because you've got the others actually are 0. If S1 is 0, that means it's 0, 0, 0. But I'm not looking for 0, 0, 0, right? S cannot be 0, 0, 0 because that's trivial solution. So therefore S1 must be 1. So therefore you figured out S0, S1, S2 to be 0, 1, 0. By just looking at the outcomes of the measurement. Of course, you have to have appropriate measurement outcomes. Otherwise, you won't be able to find this out. All right? All right. Do you have any questions? Okay, so let me give you another example before I finish. All right? So let me just erase this part. Let me give you another example. And then I'm going to talk about belief propagation algorithm that could be useful, It's a classical part of the Simon algorithm, by the way, right? The Simon's algorithm actually consists of 2 stages. One stage is the quantum stage. Okay? Just erase this circuit that gives us, potential measurement outcomes. But from that, you have to figure out the classical algorithm that uses those measurement outcomes to find what S is using this relationship, this specific relationship. So here's another example. Let's just suppose that N is 5, okay? And I'm not going to tell you what S is, okay? We're going to figure out together. So let's just, make a query and get 5 different bits, outcome of the measurement. 5 different bits. First try, let's just first try, I get the following, 1, 0, 1, 0, 0. That's my outcome of the measurement. Okay, that's the first measurement outcome. First query. Okay, first try or first query. Okay, that's my outcome. What does that tell us? What that tells us, I'm looking forward to, find out what S is. S is S0, S1, S2, S3, S4. Because it's 5 bits, right? Remember. But this tells us something. That basically tells us S0, this is S1, this is S2, and XOR S2 is 0. Okay, because the dot product is 0. I know that product of S and this sequence is 0. So therefore, if I take the dot product, that's going to give me S0 XOR S2, because the rest of them are just zeros. They cancel each other, cancel away. And that result of that should be 0, because dot product is 0. Okay? Because it appeared at the output of the measurement. I know that holds, this property holds. Okay, so the second try, let's suppose the second try, or second query, let's just suppose that I got 0, 0, 1, 0, 0. Okay? That means I have S0, S1, S2. S2 is 0. Okay? S2 is 0. Because this is S0, S1, and S2. Since there's only one 1, that means S2 is 0. But since S2 is 0, I use this previous equation to figure out this implies that S0 is also 0. Not just S2 is 0, S0 is also 0. Because if these are both 0, then you can get a 0. Okay? Now I'm trying, with the second try, I actually figured out both S0 and S2 at the same time. Okay? But you need extra try or query. Okay, now we run it again, third try. With that try, we actually get 1, 1, 1, 1, 0, let's suppose. And all of them, of course, happens with equal probability. Remember, there are, there are 16 different possibilities here, and all these 16 probabilities happen with 1 over 16. Okay? So remember, each one of them happens with equal probability. Okay, now, so I have got S1, S0, S1, S2, and S3. XOR together, right? Not the S4 because S4 is a 0, but these are zeros. I know that S0 and S2 are zeros, so that actually I can use this equation to reduce this S1 and S3 to be 0, right? Because S0 and S2 already 0, okay? So that is the reduced form. Can I determine S1 and S3 from this equation? No, unfortunately not. So I need another try. Okay? The fourth try. When I get a fourth try, I got 0, 0, 1, 1, 1, let's say. And that gives me S2 XOR S3 XOR S4, which is equal to 0. Okay? Well, can this tell us something? Well, I know that S2 is 0, so therefore S3 XOR S4 is also 0. Okay? That's how I reduce the equation. Well, unfortunately, I couldn't still figure out what S1 and S3 and S4 are by just using the equations. I'm in an extra try. Okay? So therefore, I'm going to make another run. Oops, let me just see. I have S1 and S3, right? But do I know S1 is 0? No. Oh, I see. Okay, so do I need an extra try here? That's the question. Well, let's just use these equations if we can, because I cannot accept the trivial answer of 0, 0, 0, 0, 0. 5 zeros. That cannot be accepted. So I know that S0 is 0, S2 is 0. We quality check that. We know that they are true. How about S1, S3, and S4? So if S1 is 0, then S3 must be 0. If S3 is 0, then S4 must be 0, right? So therefore, this is going to give me, if S1 is 0, then all of them must be 0. So that is not acceptable, because that's the trivial result. I'm not looking looking for that particular trivial result. So that's why S1 must be 1. Okay? Otherwise, it will not work. If S1 is 1, then S3 must be 1. Okay? Because it's tied up with this equation. And if S3 is 1, then S4 it must be 1. So there are actually two options here. Either this one or this one. And S4 is 0. Right? You either have this one or this one. You cannot accept this because you already have S0 and S2 are 0, 0. Okay? You don't accept that. But if S0 and S2 turns out to be 1, or either one of them is 1, then you would not be able to figure out which one is right. Therefore, you need an extra try. But for this particular example, you don't need extra try because you already figured out those S's. Okay, so S0 and S2 they're all zeros. S1 is 1, S3 is 1, and S4 is 1. Therefore, your final sequence here is S0 is 0, S1 is 1, S2 is 0, and 1, 1. That's your S. Okay? By just looking at the measurement results. You only need 4 tries. Okay? You only need 4 tries. Okay, so there's actually, this is kind of a nice variation of an algorithm called belief propagation algorithm. Okay, you can actually look it up on the web, and that basically solves these questions by just going through these simple equations. You solve these S's, one by one. Okay, by going through these equations, and there's a specific, nice property of this belief propagation algorithm that helps you solve this question or set of problems, in linear or almost linear time. Okay, depending on, of course, the probabilities. You can actually come up and say, oh well, I could have one of those tries to be all zeros, right? Just like in this case, right? If there's a 0, 0, 0, 0 at the output of the measurement, that's not going to give you any advantage because 0, 0, 0, 0 is actually not conveying any information. It's not telling anything, different. So that can happen, by the way, if you're unlucky. So that's why I was trying to tell you that this is probabilistic argument. There's always a probability that you will never be able to resolve S. Okay? So the approach you presented is not basically assuring that with 100% or probability 1 or certainty that you will resolve S. But with high probability, you can resolve this S. Okay? And in the next class, probably we will characterize this error and give an analysis of this algorithm in more detail.